very honored to have Dr. George W. Griffith, who comes from us from outside Route 128. He is in Idaho. It's 8 o'clock in the morning there, so thank you. Dr. Griffith has a BS in nuclear engineering from Iowa State and a PhD in nuclear engineering from North Carolina State. I'll read his bio. He was he's at the Idaho National Laboratory. He was the Idaho National Laboratory Thermal Science and Safety Analysis Group Manager and the Light Water Reactor Sustainability Advanced Fuels Pathways Lead. He worked on the Advanced Test Reactor Methods Upgrade Project to modernize and enhance the computational tools used for reactor physics and analysis. This project involves updating and validating new computational products, methods to support the Advanced Test Reactor's fuel cycle and experimental analysis. The Idaho National Laboratory worked on the Idaho National Laboratory low-enriched uranium studies to support the conversion of research reactors from high-enriched to low-enriched uranium. And his primary focus is working on nuclear projects and advanced calculations for reactor core design and licensing. In other words, I have no idea what he does. But he did author a paper, which did you disseminate that, Steve? Yeah, I sent you the email. He authored a paper last June for the U.S. Department of Energy, small modular reactors, current status, development needs, and global perspectives. That's June 2024. And that was in English, and that one I could understand. So you may find it. Yes.
I will be putting that on the group wiki.
Okay, good. Now let me hand it over to George. Thank you, George.
Sure. Thank you for the nice introduction. I can tell I need to update a little for reference. A lot of my recent projects have been about deploying SRMs and other reactor systems around, well, the world. It's been a really fascinating time to be working in the field. I was one of the team members trying to put the NuScale small modular reactor on the INL site. So very hands-on sort of work in that field and in the technology. At one point, I was a reactor engineering manager at the Cooper Nuclear Station. I'll show you a picture of that as part of the slides. So some operational experience, which has really been fun to be able to help. The reputation of the National Lab is that they are not very operationally sophisticated, and we've been able to help with that. So SMR technology, we appreciate the invite. Topic I much enjoy. Next slide. So small modular reactors, introducing the topic. Obviously, what is a small modular reactor? It's a little bit of an open question. The IAEA has a definition. Everybody kind of agrees less than 300 megawatts, deployable as individual units, built in factories and shipped. The NRC has less than 300 megawatts, light water reactors, as opposed to advanced reactors. We'll get into that in a little bit. And the DOE, small modular reactors, tens to hundreds of megawatts, and can be used for a variety of purposes. So that small building that looks like an A-frame there would be a microreactor. That might be 10 megawatts and sit on its own and work as a nuclear battery, very simple, localized, maybe something when you needed absolute certainty in your power. You were very, very remote, like a mine site. That's the application for a micro like that. The picture next to it is a unit from the NuScale plant, one of 6 or 12 in a nuclear power plant. And you can see that there's a little human figure there at the bottom right of that. And so despite being a small reactor, it's still a really large piece of equipment. There's some 80 feet high and 20 some odd feet in diameter. And so small is relative in this case. And then that picture at the bottom is a current sort of giga class light water reactor. That's the Cooper Nuclear Station where I used to work. It's a 800 megawatt boiling water reactor. So you can see they show up from sort of the size of a house all the way up to a large industrial facility. Significantly, a nuclear plant, even a full-size one's a lot smaller than a coal plant of equivalent size. So everything kind of falls into range. If you go to the next slide.
George?
Yes.
Yeah. When you're quoting the megawatts, you're talking electrical, so thermal somewhere in the vicinity of almost a gigawatt thermal for even the one that's rated at 300, right?
Yes, you get about 30% efficiency out of a light water reactor. maybe up to 40% for some of the high temperature advanced reactors.
Mhm.
So exactly. So this figure, it's a distribution, shows sort of areas where you can group things together. That's the way SMRs are. They may include some of the features I just described. They may exclude some of the features. They may, incorporate that. And it's sort of like a pickup truck. If I say pickup truck, you think of something and you can recognize one. But there may be some that are in that group, and some of them aren't, and that are close. So it does depend a little bit on the exact definition and sort of what the vendors and the utilities and the regulator want to say. Again, we're going to repeat a little: small, less than 300 megawatts, but bigger than 10. And safety, I'll come back to that, but safety is sort of the critical determining factor in my mind. The original SMRs were designed with very high safety, very high simplicity. And then they found out that wasn't good for just safety and simplicity. It was good for siting. It was good for economics. It was good for crew training. Safety has a benefit all through this. It's the critical factor in really defining a modern SMR. Slide's a little mixed up there. I apologize for that. Modular designs means that you can now install multiple reactors into a single nuclear power plant. There's some design features that have to go into that. Again, that's coming up. Flexible power generation, you can use it for heat, you can use it for electricity, you can use it to heat up salt to be stored for later, driving hydrogen production. They're being designed for those sort of applications. Economic, they're being designed smaller, right? You'd expect less inputs, less cost, simpler builds, less of a mega project. Intent is to build them as on an assembly line once the order book gets filled up. And so I have a picture later, shows a 737 assembly line at Boeing where they're assembling full-size jets. You can imagine them doing that with reactors. Small footprint, you saw the picture before, really small units overall, just in the land size that they use. They are well designed to replace fossil plants, so they're variable size. They can match what was there. And then that gives you the advantage of taking advantage of the grid of hookups that were there, the water use that was there, the environmental understanding that was there. So as these fossil plants come offline, dropping a nuke in that same place is showing to have a lot of advantages just for sustainability. And support integrated energy systems. That's the non-electric production, heat, hydrogen, other sort of applications. All these SMRs are growing up in that environment and so are good at doing that. Next slide.
I got a question.
Sure.
When you say that you're replacing other plants, so is each one of these a specific design?
Each one at a power plant would, like if you bought the, say the XE100 design, they offer a gas cooled reactor. You can buy them in units of 1, 2, or 4, and you decide what nuclear power plant you want, and it would have multiple reactors of the same design. You wouldn't mix and match designs just because the operational aspects of that would be a nightmare. And then NuScale offers the same thing in pairs. You can get 2, 4, all the way up to 12 reactors in a singular nuclear power plant. And the real trick in that is that these are designed so that one crew operates them. We currently have sites where they have 2 reactors on them, but you have 2 crews, 2 maintenance organizations. It's 2 plants next to each other as opposed to one big nuclear power plant with multiple reactors. On the slide, some more features. The simplified design, they're integral. A picture of that coming up. Means everything goes inside a single vessel, and there are fewer active components. I worked at a plant. I know more about valves and AOVs and just stuff that'll drive you nuts and get you phone calls in the middle of the night. Fewer parts, fewer things to break down, fewer things to maintain, fewer parts to keep in the warehouse, smaller supply chain. Everything about simplified is good too. Modular, we just discussed that. Designed for safety. Some of the features are showing up are below grade construction. That's for impacts, blasts of any sort. It just makes the whole system more robust to be underground. Reduce safety systems so that your cyber footprint is smaller. There's less to attack electronically. It ends up that these SMRs have very, very few critical safety systems, and they tend to be passive. Therefore, you don't need a very sophisticated computer environment to make sure those things stay out of the hands of somebody intending harm. Else, well, again, makes things simpler. And reduce size and the source term. Source term is the inventory of radioactive material inside the vessel, and smaller reactors have less material. They have, in a smaller size, they've got more barriers. So even if something bad happens, which isn't going to happen, it's harder to get to the environment, which makes them safer and easier to site. And passive, improved safety response, right? The operators don't actually have to do very much. There is actually a case at the NuScale plant where they have certified through the NRC, something bad happens, all the operators can put their hands up, step away from the panel, and it'll be okay for as long as you want. Nice feature. You can imagine that provides a lot of assurance to everybody. May be an economic disadvantage for you, but it's not a safety disadvantage for you. And the smaller vessels allow for passive cooling. So these systems tend not to have active water pumps, or water pumps would be the primary case of that. So they can run on natural circ. That's something you see in some other reactor technologies. The boiling water reactors can do it up to a certain point as well. But just having a whole nother system that doesn't need to be maintained, huge advantage. Next slide. So just to show, we talked about these are being in development. You've seen them in the news a little bit. This is the IAEA database, the Advanced Reactor Information System. Look that up on your web. You can get to a document they provide called the SMR book. And it just has a list of all the projects that different vendors from different countries are developing. And someone like me, it's just fun to go through. It's like looking at a car magazine with all the best models that year. And I just broke it down a little bit there. You can see there's molten salt reactors, fast reactors, a bunch of light water reactors, putting them on barges, all sorts of things going on at the same time. There's one in direct review by the NRC right now, which means they're serious, they have money, they know what they're doing, and they're able to talk technically. A bunch of pre-application activities are happening as well. So this is an active field of development. I'm not sure whether you see it, but my news feed every morning is full of reactor projects wanting to start. There's just one in Arizona, all across the US, all across the world. Somebody's interested in some of these projects. And that ARIS database, if you want to look at it, again, I can recommend it. It's just really fascinating to see all the options.
So is anybody pursuing small modular CANDU style reactors with heavy water moderators?
I don't believe so. And probably part of that is because the CANDU design was originally an accommodation because they couldn't make large vessels, right? You've seen there'll be a picture coming up, but like a typical light water reactor uses an 18-inch thick steel drum, essentially, to hold all the pressurized components within it, all the fuel components anyway. And the Canadians weren't able to do that. So to have a different solution, they used the smaller tubes that were pressurized inside the heavy water drum that they had. So it's a different design to avoid that. The RMBKs in Russia were very much the same thing, where they use smaller tubes to put the pressurized components and then unpressurized material around it. So in this sense, you really don't need that. And the heavy water is a little bit of a disadvantage because you just need more volume to become effective. It's very efficient for neutron use, but that's not really the thing that everybody's after with these smaller systems.
I was just thinking because of the challenge where the people are trying to build the first generation of the fusion reactors, they need tritium. Mm-hmm. And the supply of tritium seems to be peaking in the next couple of years and then going down, and that makes it difficult for getting the small type of fusion plants, the first generation kind of fusion plants, operational. And so I was thinking maybe somebody would get in the business of making tritium with these things.
Right. You could certainly make tritium as just a activation product Right? They've done that at TVA, where they built tritium for the U.S. government
Yeah.
at a light water reactor. So that might be a path to expand upon as that becomes more real. Next slide. Let's think we skipped one. There we go. Economics, I mentioned this. They're designed for a complex grid. The grid that a gigawatt baseload plant was designed to operate in doesn't exist anymore, or barely exists anymore. I know at the plant I was at, we had an agreement with all the local grid operators that the last resource to be asked to change power was going to be our nuclear plant, just because changing power to a nuclear plant is something you don't want to do. It's complex, a lot of staff, lasts a long time. Into the modern grid with renewables, wind and solar, and the battery storage systems, these reactors are having to move up and down in power, and they're all being designed one way or another to do that. And so they can follow a day-to-day cycle, they can do a weather cycle, they can help support that. And what we're finding through other parts of the Idaho National Laboratory who do the economics in these studies is that nuclear supports renewables. If you want more renewables, you need more nuclear. They make each other better. The two of them together are a better solution than either one apart. I think that's kind of a tiny story, a background fact that really hasn't gotten out of there, because you always hear about all renewables. We want all renewables. Well, if you want the maximum amount of renewables, you need some nuclear in there to help out. And that's a really neat story, I think, that comes out, because then you need less overbuilt capacity. The transmission becomes less critical. Economics are just generally better. Again, I talked about supporting integrated energy systems. Generally, you want high temperatures. That's advanced reactors, but not necessarily sized for industrial applications. A gigawatt worth of industrial applications is a lot, so you typically don't see that. Although some of the data centers are now talking about doing that, which is interesting. And modular units can be optimized. If I have 12 reactors in my power plant and one of them is dedicated to producing heat to make hydrogen, I can make that one reactor very, very efficient at doing that. It isn't called upon to do the usual electrical delivery processes that the other reactors are do. So I can optimize my plant for my specific economic environment. Modular benefits, you can deploy them individually. So I build the concrete structure for 12 units, but I only put in 4. Then as my grid grows, I put in 2 more and then 2 more. That's an option we see more in developing countries where their grid is not up to full scale yet, but they anticipate rapid growth. In the US, it tends to be better to build the plant you want and start making money early. That's just a better financial decision. Again, matched to your financial support. If I can afford 4 reactors and that's the price and the risk that my company wants to take, I buy 4. If it's 8, then I buy 8. You can optimize your build. Again, these can fall into smaller spots on the grid. If I'm replacing a 300 megawatt coal plant, putting in a 300 megawatt nuclear plant would be great. There's a big capacity factor difference. Coal plants typically run below 70%, often below 60%. Nuclear power plant runs about 97% of the time. Just they have concentrated on that and got that right. So the power companies even talk about putting in smaller nuclear plants and still getting the same power. I don't quite understand how that helps you address max power requirements, but they consider it. And being smaller, being able to be divided up, you get more predictable costs and deployment schedules and activities. And we're seeing that the improved safety could reduce the insurance requirements. That's pretty far down in the weeds, but can make a difference. Next slide. So safety features, integrated designs, we talked about, I mentioned that before. That's the idea that all the parts of a reactor to make power, to make steam, essentially fit within one single pressure vessel. There's nothing that leaves the pressure vessel and comes back except for the main steam supply, basically. So there's fewer or no pipes, right? Nothing to break, no welds to be x-rayed, no corrosion to worry about at your corners of your piping, fewer valves and controls. The pipe break accidents go away. It makes for a simpler build at a factory. At a factory builds are higher quality than in the field. That's another benefit. Having an all steel structure is a much easier engineering process than steel and concrete. When I was in college, I put myself through school by being on concrete crews. I thought concrete was pretty cool. As a nuclear engineer, concrete is not a nuclear material. It just varies too much. You look at the history of some of the plants built in Europe, some of the plants built in the US, getting the concrete right is maybe the hardest single thing. They do it at quality with the right materials in it, with the right grid of rebar supporting it. Concrete's hard. Being able to work with steel, like in shipbuilding, much easier activity. You can put them underwater. Longer release paths, that's trying to get the radioactive material in the core to the environment. If it has to go out of a big pool, like in the NuScale plant, that's just one big filter that gets in the way of that. So you don't have as high a consequence from any event that does happen. High thermal mass in a large pool of water. And it's really hard then to be doing sabotage, things that are risky when the whole thing's underwater and protected. And we talked about passive operation as a safety feature, reduced active components, powered valves, pumps, that kind of thing. Fewer actions are needed by the crew. There's just less for them to do, less for them to know. Makes it easier to do the right thing. Less maintenance and components, and fewer safety systems, smaller cyber target. I mentioned that.
Another
Next slide.
question.
Sure.
You're talking about steel containment. What about radiation damage?
Generally, there's enough of an offset between the fuel and the vessel that's not a particular issue. There are concerns about it. It's being studied pretty actively with the current fleet of reactors because they've been in service for 40, stretching to 60 years. And very low doses can have effects on where copper goes and embrittlement goes. That'll be evaluated in the future, but they're actually designing these things with their low power density, some offsets. The pressure vessel itself is generally well protected in the sense that we understand how steel works. You can monitor it, and it's within an engineered system that you can know is predictable. Concrete tends to degrade in other ways. Just high temperatures cause concrete trouble, dry out, and stuff like that. It's a little less easy to survey and maintain.
Yes,
I'm
a
big fan
is there
of
a
steel.
maintenance problem then?
There are, I don't know that it's a problem, but I think the activity of verifying you're still okay can be difficult. Hey, I'm in a containment vessel and there's a big wall of concrete. Is that wall still doing its safety function? Well, what's that mean? Okay, I'll go check the density of it. I might take some samples of it and see if the chemistry inside the concrete's changed. It gets hard in that sense to verify something absolutely the way the NRC likes it to be. I think it's all things that can be overcome. We obviously use concrete in all sorts of civil structures, but it's more difficult than it would be if it was, say, a piece of steel. So in a modern design, using steel is a good idea, I think. There's still lots of concrete in the nuclear plant. We'll see that when we get to the NuScale design. But again, you go back to like maybe the shipbuilding industry. If I was to build a ship, I can do that. I can repair it. I can cut pieces out. I can replace pieces and know absolutely it's going to be fine. That's good. Anyway, my take on it. Next slide.
Thank you.
Oh, I wanted to ask a question about
Sure.
Pressure. So the light water reactors require the water be under very high pressure so that it doesn't boil. And that does have an effect, I think, on, different kinds of, release problems, pipe breaks, etc. Does the Idaho National Laboratory, or do you have any comments about, the advantages of other forms of reactor, not light water, to relieve that problem?
We work with all the different kinds of reactors, and I do have some examples of that coming up. I think in the grand scheme of things, the If I wanted to build a reactor that made megawatts of electricity as cheaply as possible, I would go with an LWR. If I have multiple missions for that reactor, I would start thinking about high temperature systems that are gas cooled, molten salt, liquid metal cooling, where that high temperature has a specific benefit. I think the safety case can be made in either system. I mean, we've learned enough about light water reactors now that they can be designed as safely as they need to be, which is what we've seen. Like the NuScale reactor has an accident rate of 1 × 10⁻⁸ per year. That's so low that it started getting into the, do you actually care about that? The NRC has a hard time with that because that's so low it falls out of their likely events categories. How do you license that? So I think that with our modern understanding of things, you can build a safe reactor with any of these technologies. I think you use those advanced materials and reactor types when there's a real use for it. And I think those uses are coming near term, midterm.
If you're trying to integrate these things into a renewable dominated grid, they have to be able to cycle up and down or be throttled and stuff like that. Is that part of the design feature of an individual one, or are you talking about just having a whole bunch of them? You can kind of pick and choose how many you want to have on the line at any given time.
Both. For the application, say a NuScale reactor's got 12 modules. I have a seasonal variation on the power I need, so maybe I'll turn 2 of them off, just save the fuel. The rest of them I might throttle throughout the day, or maybe 2 of them I throttle hard and let the others run at 1 speed, 1 power level. NuScale is sort of unique in that their way of controlling power is almost instantaneous, but they just dump steam to the condenser. So it doesn't enter into the energy generating system. Obviously not the highest efficiency use. Efficiency is not the problem in a nuclear plant. It's usually operating costs, matching the grid. So that's actually a reasonable path for them. Other reactors are built with lots of control rods, lots of power controlling equipment. And they almost reach that point where I can just throttle them up and down. There are applications that I'm not supposed to talk about where we 100% know that reactors can just be throttled up and down real time, almost without concern. So it's certainly possible. It's not probably economic in a commercial system, but they can do that.
You would keep the vessel hot. You wouldn't cool it, right?
Correct. As long as you're going to keep producing power, you expect to make power later. You would leave it critical, hot, and pressurized.
So that helps with annealing any kind of radiation damage to the steel and things like that.
Yeah, a little bit. There's always some of that going on in the background. Typically with an LWR, it's low enough temperature. It's not a big deal. Some of the HTGRs, it is. There's actually a limit, right? We all design reactors with materials that are well understood and have ASTM code cases. Some of those code cases for steels do not last long enough to be the lifetime of the plant at the temperature some of those reactors get to. And so we've seen some vendors say, hey, my reactor is only going to last 7 years. At which point, not only am I going to replace the fuel, but I'll replace the vessel. Again, an advantage of the smaller reactors. But that's largely because we don't understand or don't have a proof that they're okay. I think as time goes on, they'll do studies and say, okay, it's 14 years, it's 21 years, it's 50 years. They'll figure that out pretty quickly. I know at my plant, it drives you nuts. There's so many things to check. There's big entrances for the cooling water. It comes out of a large nozzle. We talked about chemistry and steel. Hot water and anything is reactive. Hot water, steel, and radiation tends to cause cracking. So during an outage, there were guys crawling all over our reactor with ultrasonic probes looking for cracks. And then there were ways to mitigate those with overpressure. You'd have guys walking around the plant putting ultrasonic detectors on every corner of a pipe. All right, so if it goes down, it takes a 90-degree turn. I'm going to check that 90-degree turn to see if I'm getting erosion.
If you notice, I said I worked on the everything but the control room.
Yep.
Then after we had a few accidents, the Nautilus and the 3 Mile Island, I said, oh my God, because I went to work in the business just to find out if these things were safe or not. Oh yeah, everybody was designing it safe. As a matter of fact, it was so safe that it caused 2 accidents.
Right.
Like on the submarine, for instance, it did have backup power to restart the thing if a leak sprung, you know?
Right.
You know
Yeah.
what I
And
mean?
it's every technology matures. Certainly they learned a lot about operating commercial reactors and those lessons learned. And you'd probably be impressed by the changes between what you had when you were working there and what's at the modern plant. Um, IMPO and some of those other organizations have really ground that to a smooth river rock.
Right. Well, I gave a talk for this group years ago on the safety of nuclear power, you know, and I used
Yep.
your organization and the DOE. Now I'm
Yep.
so old, I went and looked up the AEC and the NRC, and you know, they
Yep.
don't exist anymore.
Yeah. My favorite's we have a code called RELAP, which is a systems code that just shows, hey, I've got a reactor system and I break a pipe here. What's the response of the whole system? And it's like, okay, well, I can engineer that, but how do you verify it? And so they went out and they built a full-size model of a reactor with a nuclear core using old Navy parts and pumps. And then they built it and put a great big tank on it where they could jump all the exhaust. And they went out and broke pipes and watched the way it worked and verified it. We've got multiple billions of dollars in designing those codes and knowing that they will work reliably enough to do what we need them to do. It's a fascinating process, all the testing that's gone on, just so we can do the designs. Whole nother presentation for you guys to think about later. Back to this, some safety features. Maybe this will have some resonance. Smaller reactors have smaller source terms. Talked about that. Physically smaller cores and power reduce the fissionable materials. Just less stuff to get you in trouble. And separating power across the core reduces the release fraction. By having these things separated at lower power densities, they're just less of a threat to do something untoward, right? Particularly lower power densities, which gives you needing less cooling requirements, and it's a lower challenge to the cladding, to the vessel, to everything else. The heat is just less. And this is mostly for water-cooled reactors, again, as was noted. They tend to have more water in them or more coolant in them compared to a large commercial reactor. They have increased thermal mass, so they react slower to any changes. And it's easier to provide long-term cooling. The actual inches between the center of the core and the outside of the core where the heat has to go is smaller. Makes everything easier than having a larger core. And smaller containment sizes, easier to provide passive cooling for is probably the big one on that. So just these features, these are safety features that has knock-on features that prove to be beneficial. Next slide. So this is IPWR, Integrated Pressurized Water Reactor. So this is the next step in the reactor evolution, half step maybe. If you look at that, there's sort of an inner structure there that looks like a big thermos turned upside down. That's that integrated pressure vessel. Everything in a reactor fits in there. The steam generator, the control rods, the pressurizer, all those components that are separate in a conventional plant have all been put in that single vessel to make it simpler and easier to do, factory built. For reference, that little red part at the bottom, that's the core, right? Everything else is just to support the core, right? So like your whole body built to support your DNA, that's the same sort of situation with the reactor. It's all supposed to keep the core happy and operating. Next slide. So integration, picture on the left would be a conventional PWR. The green objects are the pumps. The big vessel in the middle is the pressure vessel where all the fuel and the control rods and everything else goes. There's a pressurizer, all that piping to connect things, chemistry set. All of it's built inside that big concrete dome that's lined with steel, as opposed to the IPWR where everything fits inside the steel vessel. You can see there's just less to worry about breaking, corroding, failing, less to do maintenance on, less to do testing on. Next slide. So another graphic to show how these things have gotten simpler. That list above is all the emergency systems of the PWR. The one below it is all the things that show up in and I say typical, there's a particular vendor out there I looked at to do that. But you can see that number of things I have to worry about went down by more than half, right? So theoretically, I've got half the engineers, I've got half the maintenance guys, I've got half the testing, cuts my costs in half, maybe, hopefully. So another way to look at that. Next slide. Other features, they can support blackout grids. This SMR can be started up from cold, black, and can help restart your grid. My boss, when I started the nuclear plant I was at, one of his first jobs at his previous power company was, how do we black start? Right? Our grid goes out, nobody can help us start. How do we get it going again? And he looked into it and said, we can't. And so they had to go fix that. That was one of his first big jobs at that power company. If you got no power, it's hard to know what you're going to be doing to get the system up. SMR can support that. They can operate in island mode, right? The grid around them comes down, but you have a community nearby, a data center, a defense infrastructure system, something like that. They're small enough that they can support just that smaller grid. The underground construction we talked about, impact risks go down, can't be hit by an aircraft, those sort of things. And they're physically small, which is nice. At our INL, right, we're just a little bit smaller than the state of Rhode Island. Even on that side, it's nice to know that these little reactors have small footprints. It's just less stuff to get in the way of the DOE mission. Surprisingly big deal. And again, the truck down there, that would be how you'd haul it. It's small for a reactor. It's not a small thing. Next slide. HTGRs, this is high temperature gas cooled reactors. Fascinating pieces of equipment. They're really safe just inherently. It is helium cooled, so no phase change from steam, runs at very high temperatures, has a large low power density core, so they're very safe, lots of thermal mass, so they react very slowly. Everything about them is just kind of, I'll say gentle, except for the fact they run at 850 degrees C. And the really interesting feature is they run with triso fuel designs. And what that is it's a tiny little kernel about the size of the ball in a ballpoint pen that gets covered with pyrolytic carbon, silicon carbide, and then more structural carbon. And what that does essentially is it makes a little tiny mini reactor that goes into a stack to make a fuel pellet that goes into your reactor and then operates conventionally. So essentially you've sort of designed a tiny micro reactor to keep the rest of your reactor safe. They're really safe. They operate at high temperatures. They're very reliable. They're a little expensive, right? So when you hear triso fuel, think safe but expensive. I'll show you some other examples of that. Interestingly, these go in a pressure vessel that's made of all concrete because there's no real pressure there. Very little radiation because of the large size. They tend to run with concrete, and they're not even containment structures. They're just separation. It's a different concept. Next slide. Molten salt. I don't know if you've heard about these ones particularly or not. It's using salts that are made up of 2 or 3 different components, fluorine, chlorine, beryllium, to make a low temperature salt, similar to the solar salts that are used in solar concentrators. Very high temperatures, above 600 C, no pressure. The stuff has no vapor pressure, so it doesn't make a pressurized system. Very high thermal conductivity. Once you have a smaller system, the coolant, despite being a salt, is essentially non-reactive as long as you pick reasonable materials. You could have fuel dissolved directly in the salt, so uranium compounds that are salts themselves inside the salt liquid flowing around. You could just suspend those triso particles I talked about, or you could have a conventional fixed fuel just cooled by molten salts. So a lot of flexibility there. Oak Ridge ran one of these in the early to mid 60s. Proved to be sort of, sounds like everything's great about that, and they're exploring that rapidly now. Is there a question?
Yeah, now that would make a good tritium breeder because if you put lithium and beryllium in there, you make a lot of tritium.
Right, and they actually, that's enough of a concern that it's the opposite problem. They make too much tritium, so they tend to do isotopic separations not to get that reaction. Otherwise, suddenly your reactor is just full of tritium to the point where it's a problem. So yeah, that's entirely possible. And they talk about doing this online where you could just constantly feed in a drip of uranium or thorium and then pull out the fission products, and it would just sit there and percolate continuously. You wouldn't have outages. You wouldn't have fuel activity so much.
I wonder
So that's an
why all
interesting
these
thing.
people are worried about shortages of tritium aren't aware of this. I said,
Yeah, it would. This could turn it around pretty quickly.
yeah.
I'm not. Yeah, it'd be interesting. I don't know that I've ever seen anybody do a study on that as a uh, linked fuel cycle, but it would be interesting. We have people who do that. Next slide, please. And then liquid metal reactors. These are the kind of reactors, probably if you heard advanced reactors 15 years ago, this would be what it would be. And they're cooled by either molten sodium, potassium, or lead bismuth eutectics, right? Liquid metals conduct heat very quickly, allow for very dense power systems. They have an interesting property that they proved at INL with our experimental breeder reactor 2. It was about a 50 megawatt reactor. They got it fully up to power, making power, and then they just shut everything off. They closed all the valves and locked this reactor at full power inside its vessel. And they found out that it would heat up a little bit and the fuel would expand a little bit. It would go subcritical and it would just shut itself down and the heat would go away. So literally the worst possible thing you could do to this reactor, they did to that reactor and just did fine. It was, and I think it was even an unexpected result. They kind of knew it might happen, but they didn't design for it. There's pictures of the control room at the EBR2 when they did that test, and there's about 50 people in it from all over the world just to watch that. So an inherently safe design if you get it right. There's some experience in there. There's some lessons learned you got to know. I wouldn't want that to be the first reactor type of company built and, and believed all their results without a lot of testing. It's a demanding technology, but it's a good technology. And again, these are called fast spectrum. That means the neutrons, when they fission, they come out of the uranium atom at high speed and they stay going very fast. Reactions are small, they travel a long way, sort of homogenizes the whole core. Whereas in a light water reactor or with carbon or heavy water, those neutrons slow way down and tend to interact more with uranium than anything else. It's a little bit different physics. The time frames are a little different. Again, a whole nother topic if we want to talk about it. Next slide. We talked about safety, reducing the size of the siting requirements and things. There's an emergency protective zone right now that's required in LWR, and it's 10 miles. You have to be able to control who's there, whether they evacuate, sort of be able to display control over that area for safety reasons, and a 50-mile boundary for controlling agricultural products, because if something gets out, strontium goes into milk, not a good thing. Into the meat if the animals eat it off the grass, kind of thing. So these EPZs are very large in a conventional reactor and require a lot of work and design and coordination to manage. The EPZ on modern SMRs are being anticipated to be the fence line for the plant, right? So, oh no, the plant down the road is having an accident and everybody gathers around and grabs a hold of the fence to watch. Those people would be perfectly safe and not an issue. Right? They wouldn't even have to have them removed. It's just, that's okay. You can watch. I find that that's a really reassuring thing for people to understand, right? It gets them over a lot of that fears of Chernobyl, of Fukushima, of other things. And I think it's a very big deal. Fukushima was a hugely distressing fact to all those people there because they had to be evacuated and removed, not because they were harmed, right? That's not an acceptable choice. That making the EPZ small is a really great feature of modern SMRs. Next slide.
I got one more question on that one.
Sure.
I was on the City of Austin Electric Utility Commission when I was a research staff at University of Texas. And we used to have a public meeting every month, and people would come and, mostly bitch about their utility bills and things. But every once in a while, you get somebody who came in with some crazy ideas. And apparently there was a student newspaper, it may have been the Berkeley Bar, but I'm not sure. But it was a student newspaper, UCal Berkeley, that put out a story about the fact that electricity coming from a nuclear plant would be radioactive. And so this guy, I'll call him Paul, he presented this to us at the commission, and I got in trouble for putting him in his place. I said, Paul, you're radioactive, I'm radioactive, the entire universe is radioactive. The only thing we know is not radioactive are electrons. And
Right.
there was an idiot from the local newspaper in Austin who put it on the front page. It was below the fold, but said, Commissioner says everything radioactive. We got calls like you wouldn't believe about people who were worried about things. The
Yep.
suggestion that the newspaper had, the student newspaper had, was put electrical tape over the outlets that weren't being used.
I like that.
Right. So how do you
Well,
get over that aspect? Because you know, you have these people who are just, they have a utter fear of nuclear, the word nuclear.
right.
Yeah.
I think it's being honest with them and direct. These are the things I know. These are the things I can do. These are the things I don't know. These are the things I wouldn't do. And just being in our world, INL, we really do have a luxury in that. And then we can just be a neutral voice about this. We know a lot about it. We tend to think it's good because it's good, but we'll tell you why. And so we just try to bring that sort of, we're not here to sell it to you. We're here to tell you what it's like. Education seems to be the way around that. The few folks I've seen who've come up and wanted to be disruptive of processes tend to be just really confusing. You know, hey, you're looking at building this power plant at INL. We know how bad the government is at regulating. Look at how the prices of eggs have changed. I worked for the Federal Securities Department. That was terrible. Therefore, we shouldn't build a reactor. You know, it's just got, well, okay, none of those are on a logical chain, but fine. You know, let's sit down and talk about what your concerns are. And you try and deflect it like that. So it hasn't been too big a problem, especially lately. It's a bipartisan topic. For reference, though, for Austin, just about the highest radiation area that a member of the public can get into is the Texas State House, right? It's full of, it's made out of sandstone. It's full of uranium. So anyway, security benefits, this does come up. SMR is being, sorry?
Right? They get the radiation.
So we find that, like I said, safety has follow-on benefits. Security is one of them. It also benefits from being a modern design. SMRs would be hard to get to things that are safety related. There's very few safety related things. They're being built so that getting to them is hard. They're being built with security in mind. They're underground, all sorts of things that just make the safety case easier. And it's a little hard to talk about because you get into security ideas and nobody wants to talk about them too much, but there are a lot of benefits in that sense here. Next slide. Multiple units, sort of hinted at that. There's just a list of some of the different designs being worked on right now. The red numbers indicate that they come in multiples. The XE100's 4, NuScale's up to 12. Kairos right now, I think they're going to come in pairs. The whole tech is a little bit of a single unit, so there are some variations. Benefits, lower cost, progressive deployment, we talked about that. Operational flexibility to meet the demand of the grid, alternate uses. Yeah, the things you would expect by having the option of multiple units. That's a picture of the GE BWRX 300. That's probably the next SMR to be built. They've got one going up in Canada, which will be on in 28 or 29 right now, I think. Next slide. Factory built. There's that 737 production line. You can imagine those big thermoses rolling down an assembly line just like that. Picture on the left is a conventional build in the field. It's actually a Chinese plant. I worked with some Canadians who told me that every one of those tower cranes that you see up had better be doing $1 million worth of work every day or you're wasting money. You know, I look at that picture, it's like, oh, it's a lot of work every day. Benefits of being in a authoritarian regime that you don't have to care. Flexible operations, we talked about that a bit. Steam systems are built to allow rapid changes in power, multiple units, increased temperatures in advanced reactors to better support industry, increased value products, right? Electricity is a great project. It's sort of like groceries and gasoline. The margin isn't all that high though. but for hydrogen, ammonia, liquid fuels, drying out paper products, chemical processing, concrete, desalinization is an ever bigger deal, district heating in a lot of parts of the world. All of those are benefits that nuclear energy, not necessarily nuclear electricity, can be used. And it's a useful and dispatchable and applicable technology for those sort of applications. So good stuff for these reactors to be applied to, especially the advanced ones. Next slide. This is the NuScale Voyager design. This is the one we thought we was going into the INL. It's a half slice. So you can see on the left side there, there's sort of 6 bays. That's where 6 of the reactors would go. And then the mirror side would have another 6. That's where they would operate. The equipment on the right is where you go over, you grab one of those reactors, you pull it over, put it down, disassemble it, refuel it, put it back together, and then take it back to the other side. That black object at the bottom of the pool to the right, that's the spent fuel storage cells. So big crane overhead gets a lot of use. It's an interesting way to operate. It's different than a conventional plant. And with 12 units, you'd always be up 95% of the time, even if a reactor was being going through refueling or maintenance. So your predictability goes up. Interestingly, rail, truck, or barge shipping, there's natural circulation in this one, no pumps. Everything's passive about it. Again, you see 28% efficiency. They're not pressing the technology in that way. It's conventional UO2 fuel, just like you would have in a modern reactor. And the process for disposing that is exactly the same as we have now. Right now, you let it cool for 10, 15, 20 years in the pool. It comes out, it goes into dry cast storage. You put that on a very large concrete pad next to your plant, and you leave it there until the federal government figures out what they're going to do with it. We had Yucca Mountain that was designed, built, I think was technically achievable, somewhat like the WIP facility, what the defense agencies tend to use, would have been technologically successful. Politically, it was not. There was a big report that came out from the Blue Ribbon panel where they went and looked at what the lessons learned from Yucca Mountain were, and they basically said we should do it again, only take into account the end result better. Sort of a dissatisfying result. European nations have ways to do deep geologic disposal of fuel. It's certainly technically possible. The Dutch have deployed that. Other countries are deploying it. Switzerland will be deploying it. So I think it's a technical solution. It's a political problem now. Recycling is possible. There are benefits to that. You recover the fissile materials. You take the bad stuff that's going to decay away quicker, separate it, manage it differently. It tends to add expense to the system. There was concerns early on in the nuclear power history about uranium supplies. You could look at it and go, well, we're going to run out of uranium. And then they looked and they found some more. And then they looked and they found some more. And so the price, there's a scale where if you pay more money, you get more uranium. And then the Japanese figured out that at worst, for $300 a kilogram, I can get uranium out of seawater. And so now there's a cap on how expensive uranium can get. And we also know that there's essentially an infinite supply of it. So the reasons to recycle have changed a lot. We may or may not eventually adopt some of that technology. It's always a problem because then you separate plutonium, which is a proliferation hazard. There's ways to manage that, but it's still difficult. Anyway, so that is, and I do wish, talking to the public, that I had a solid answer for exactly what that solution was going to be. There is a solution. We haven't implemented it yet. When we do, I'm not sure when that'll be. Probably not during my career. Admittedly, I'm gray-haired, so maybe that's not so bad. Next slide.
Oh, I had a question about the
It's 11 o'clock.
waste issue.
Sure.
Is it true that fast reactors would produce much less waste or much less dangerous waste?
I don't know about dangerous. They can produce less because they're more efficient. So if I've got a high temperature reactor operating 650 degrees C, it might run at 40% efficiency. Therefore, I get that jump in electrical production, I can burn essentially 25% less uranium to get the same power. So that'll be less in that sense, and it's more efficient. The fission products are going to be the fission products. The range of physics we deal with doesn't really change how that process goes. So they're all the same fission products. Now, having fast reactors, I mentioned that they stay high speed, and a fast reactor, they go farther, they interact more generally in a homogenized core. There is some additional breakdown in materials when you do that. At the same time, a fast reactor tends to activate like uranium-238 more, makes more plutonium-239, tends to activate heavier elements. So you get more of you change the character of the waste a little bit. And I'm not sure it's to the safer. Now you can do things like take it out, separate it out, put those bad actors in a fast reactor and burn them up by fissioning them. And then they'll only last 30 years or something like that. So there are processes where you can burn nuclear waste in a fast reactor that you can't really do in another system, in a light water reactor system. And again, all entirely achievable. We've demonstrated that all. They demonstrated a lot of it at INL. Is it worth the expense, or is it better to just bury it? That's part of the reason why we haven't solved that problem. Yeah.
There was a professor Cohen at the University of Pittsburgh, as a geologist, geophysicist background, and he made some analysis that showed that if you dug holes in the ground randomly and just threw the waste in there after keeping it up above ground for maybe 10 or 15 years or something to get the high activity stuff out, but it wouldn't be any more radioactive than the average soil. And that he claimed that, after, I don't know, it was 1,000 years or something, it has eroded away. It would be just equivalent in level of radioactivity to the average soil, even less than uranium bearing soils and stuff.
Yep. I think a lot of those cases exist.
That went away because it was considered extreme, but in reality, compared to keeping these things for 1,000 years in concrete casks, because we can't have the political will to dig a hole and put them in one place, spread it out all over the place and let everybody share it.
Right. Yeah, we have a lot of different ways to think about it.
He was at a University of Texas lecture series that we put together under the Society of Physics students, and we got bad local press from the university, but
Yep.
Otherwise it was very popular with the students. So
I
if you
believe
get
that.
the right level of, as you said, education, I think, but you have to start it early. You can't just
Yep.
try to go and say, we're going to put a reactor down the street from your house. That won't work.
Right. And that's actually one of the reasons that company came to INL and said, we want to build on your site, was because they knew everybody was familiar with it. There would be very little disagreement with it. Just made it easy. This is the Kairos molten salt reactor. They actually are building their demonstration reactor at Oak Ridge right now. This uses those triso fuel particles I was talking about. You can see that little 200 micrometer sphere at the center. That's the uranium dioxide. Then around that would be carbon, then silicon carbide and more carbon. Makes that little tiny mini reactor. And then you put those into a compact, goes into the fuel. The reactor's there on the right. The coolant flows from the bottom to the top through the reactor. It's molten salt. Did I mention what kind it is? No. Relatively small reactor, 140 megawatts electric. These guys have been making excellent progress. It's fun to see them. You can read about them on the NRC website. So that's the molten salt example. Next slide. This is the next step, the BWRX 300. It's a boiling water reactor that's been simplified from the one that like I worked at. It uses UO2 fuel of low enrichment, less than 5%. We have a supply chain for all of that. 300 megawatts, so on the larger side. If you owned a power company and you wanted to deploy the next generation of technology, but not go crazy and do something that's really and truly new, this is the next step, like the new scale design. That's kind of the reason why I think they're being deployed early and tending to have success in the market right now. Next slide. TerraPower Natrium. This is one that's going in Wyoming. driven by this site. It's about 2 miles down from a coal plant that they're planning to retire. They'll use all the electrical equipment from that coal plant to reduce the cost of this plant and reuse the staff, the facilities, the local benefits for that community to put this one in. This one's really interesting in that it's a 345 megawatt electric, so a little big, sodium cooled reactor, but it fills up 2 great big tanks of molten salt. That's the red and the orange structures there to the left. And the idea is that they would run the reactor at one speed, one power level continuously. And if the grid didn't need it, they would tend to heat their salt up and store the energy. And then when the grid needed the energy, just pull it out of the salt at up to 500 megawatts an hour, 500 megawatts for 5.5 hours. So sort of a way to separate the reactor from the grid from the rest of the system. They're looking at licensing that to make the licensing space very small. And that's a really creative option to have there. So a little mixing of technologies to address the grid that we have now. Next slide. And this is the Oklo microreactor. I've worked with these guys. They're looking to build at INL as well. It's that A-frame structure, 4 megawatts. It uses heat pipes to get power out of the core. So it's very much based on a system similar to space reactors, uses metallic fuel. It's all in a great big block of stainless steel, has a Brayton cycle on top of it. Very creative design. Again, very, very small. All those forces that created SMRs, you wanted less inputs, more reliability, safer. If you keep that pressure on the designers, they end up with these micro-sized reactors because they make them smaller, safer, simpler again. And so this is that next step in the evolution as well. Next slide. So SMRs are responding to a complicated environment, our modern grid and its changes, cost, schedule, uncertainty, safety, all are being addressed by different vendors in different ways. They offer increased safety through physical and design features. That allows for additional benefits in security, siting, economics, the emergency protective zone, cybersecurity. All of it works sort of as a benefit on top of itself. It's a multiplying effect. SMRs are being licensed, deployment plans are coming into place, economics are being studied, the market is developing, but that market is very rapidly changing as well. So it's hard to know where we're going to end up with it. We're still figuring it out. Next slide, I think, is my contact info. I'm around. I take questions. You can come look at our site at the inl.gov. Look at that ERA site at the IAEA. I obviously find it fascinating. I have a lot of fun with it. It's a really exciting place to be right now. The last slide's the INL one. Yep.
Well, let me thank Dr. Griffith for a wonderful talk.
Hold on a second. He's got one more slide.
One more slide? Oh, okay.
Oh,
Sorry.
yeah, that's just some background slides if we had needed it. These are the pressures of like building a modern gigawatt plant like the ones that just opened in Georgia. We've seen long times to license the new technology, 10, 15, 20 years in the case of that. Large projects are difficult to manage, so you want a smaller project. Large plants require a large grid. You can't put one of these in Uzbekistan. We found that out. Long construction times. They're difficult to finance. You can finance almost anything as long as it's predictable. If you want to go in and finance something and have unknowns in it, then the finance guys stress a lot. And the energy markets are changing. That's how we closed on the rest of it. And again, there's that picture with all those cranes in it. It's supposed to be doing $1 million of work a day. So interesting. All right. Any other questions?
Yes, could you, the hot issue right now is both supply and demand. You've talked about the supply side. How is this going to match up against the prediction, which I think is wrong, is that we will have between a 25 and 50% increase in power needs. Let me give you an example. When Henry Ford, most recently with DeepSeek, it looks like they've turned this into a high volume, low margin business. And when Henry Ford did this with the Model T, which was from 1909 to 1929, petroleum use increased 5 times, not 25%, 5 times. If the new power between the cars, the self-driving cars and electric cars and the AI power needs, what is the real anticipated power supply needs, and how do the SMRs address this large deficit that we see coming?
Yeah, it's an area that people are getting into actively. I see my colleagues and myself everyone some of the time dealing with the data center guys. They have essentially an infinite attraction to power. You see reactors being restarted. You see them going into cooperative business directly with reactors to supply their data centers. They see a huge growth in that to support AI. Well, back when I was at the nuclear plant, the big thing was ethanol. Right, I was in the Midwest at the time. We were going to see ethanol production was going to go up 5 times, like you said. We're going to have huge demands on energy, and people started to get ready for that. And then found out, do we really want to compete with food? Are there more efficient ways to do it? What do we really need? And that peak moderated. I think that same thing will happen here to some degree. These data centers being mega structures that just expand and expand and expand. Well, because of the energy demands and the cost of that, they're going to modify how they build those. They'll use more efficient chips. They'll cool them differently. They'll do different things. That peak will tend to go down. I think they'll run into the point where it's, well, power for my AI or power for your air conditioning or your heater. Well, who's going to win that one? I bet I know who's going to win that one. So I think the net effect will go down. I think electric cars are going to continue to put pressure on us. Electrification in general seems to be happening. So power is coming up. I wish I had a better story on these reactor types and that they would be here in 5 years to meet that peak. I think we're looking at 10 years, maybe a little longer, before they start meeting that peak. So that transition's being evaluated. Do I take my coal plant? Do I convert it to natural gas for 5 years as I build a nuclear plant? Not a bad plan. Do I build a gas turbine plant to replace my coal plant and then build nuclear? Do I keep them both then so that I can handle the rapid rises and falls in data center requirements? That transition hasn't been well worked out. And I don't think, and part of the problem is we don't understand what the inputs to it are, like you said. But I do think the supply of SMRs to help meet that, it's going to be a little slow. But then again, that's why we're restarting nuclear plants right now, and other things are being done to accommodate that transition.
George, this is David Kahn. I have one other question.
Can you
for
hold on a second, please, David? We have 2 people who have their hands up.
I couldn't get my hand up to show. I don't know. Yeah.
Okay. Ted, what do you want to go ahead?
Yeah, thanks. Has anybody proposed taking one of these small modular plants and inserting it into the footprint of one of the old reactors that are either potentially being extended lifetime or being considered to be dismantled and stuff? Because it would seem like you have everything there easy to get it up and running, because you've got a site already, you've got the horns going off on the regular basis to test the warnings, and you have plenty of land set aside for things like these spent fuel pools and spent fuel casks and stuff. Has anybody proposed that? I haven't heard that.
No, I think the practical approach would be to build one adjacent to an existing facility. Then you take advantage of their grid and their ultimate heat sink, that sort of stuff. Actually, reusing equipment is really difficult at a nuclear power plant. It has to be re-engineered.
No, not so much not so much reusing the equipment, but sitting, because a lot of these sites, for instance, in Seabrook, New Hampshire, they designed the site for 2 reactors. They only built one. They started building the other one in the Clamshell Alliance, which was a local group of activists, anti-nuclear activists, actually mostly anti-nuclear weapon activists, but they were co-opted by some of these people into also opposing the reactor. So there's another site there. You could stick a plant right
Yep.
into the spot that was set aside for the second reactor.
Yeah,
I haven't heard
and they
about
are
it.
considering that sort of thing. That some of the plants got, they call them early site permits,
Yeah,
where I say, hey, this is a site I want to build a reactor at. I'm not sure when I'd build it or what technology I'd use, but I've evaluated and it's safe for a reactor. And they got licenses for that. So some of those exist. Like you said, there are plants with more sites with more capacity, and those are being looked at. The one I think is most interesting is the coal replacement one. You have all the same benefits. There's more coal plants coming off. There's no power demand for that. So that's another one where that's being looked at actively.
but in New England, we pretty much already demolished all the coal plants. There's, I think, one
Right.
left functioning in New Hampshire, small one.
Yeah.
The big ones are all gone. The
Yeah.
sites are there, and people are talking about using them for making wind turbine blades or you know, something associated with green energy, but mostly they're just spent empty plant sites.
Yeah. I'd look for where they have still maintained grid access.
No, they still have
Probably
they still have the grid, and there's a huge site down in Somerset, Massachusetts. It was a giant coal plant. It was like 1.25 or something like that gigawatts electrical,
Yeah.
and they just leveled the plant. It's gone. So
Yep.
Carl,
Let's
you're
see.
next. I believe, I have my hand up and also David. So go ahead, Carl.
Yeah, mine is quick. George, is there a way we can gain access to the slides you showed us?
Yes, actually,
yeah.
I'll answer the question. I'll be posting them on the wiki site shortly after the meeting today, by the end of the day today,
Oh, very good, thanks.
along with the paper that he's written. Okay, my question. Suppose I have 10 neighbors in the area, and we all decide we want to put in a small nuclear reactor to provide electricity to us to take us totally off the grid. What type of expense would be looking into, and how practical is that? And then I guess the next one would be, suppose the town of Lexington with what is it, 30,000 people decide we want to put in our own power plant. What are we talking about in costs and practicality here?
The new high school.
Yeah,
Yeah,
30,000
new
people.
high school.
So yeah, say that's 30,000 households. You need 300 megawatts. That's an SMR. The one that we're anticipating putting in at our site, which was going to be in the 600 megawatt range, was going to be about $5 billion. So cut that in half, $2.5 billion. You can be energy independent. They are expensive projects. I would think for a small community or very small community, I would be looking at those micro reactors. It's nearer term. I could buy them 10 megawatts at a time, have a big football field full of power units that have grown into place as I've needed them. You'd start using them as backup power or baseline power to backstop your power, and then expand the use of them, say $70-80 million a unit, that kind of thing. So there's a way to build up and get into that. Starting small is easier with regulators. It's easier with your utilities. The utilities are actually the hardest part, I found. INL works with one power company. It makes it very difficult for us to work with the vendors and their requests. So I think in the Northeast, though, you've got reasonably flexible distributed energy policies. So you could probably fit one into the grid without problem. Big problem.
Times it's expensive.
David has
Okay.
Belmont, not Lexington.
I have one question. In the old days, you know, for the big power plants, and as I thought, we used to have to do an environmental impact statement. And I worked on some of those at Stone and Webster with the guys. And anyway, long story short, the question is, when you have these small portable power units, do you still have to do an environmental impact statement, you know, for the community?
Right. You do very much do. The licensing is a federal action, so you're required to do NEPA, which requires an environmental assessment. The neat trick is if they are small enough and they have such a small impact, they come out with a a FONSI, finding of no significant impact. And so basically it's like, okay, well, we don't think it's a big deal, go ahead. And they don't particularly watch all over you in those sort of cases. And we've had that result from some of our planning here at INL. So you still do it, but it's a graded approach, and the result of those analysis is much less impact. So you don't have to do as many mitigating things. It's much easier.
Is it possible to make a multi-kilowatt?
You can. I think the smallest reactor, critical fission reactors, you could put your arm around, right? It's about the size of a trash can. You can make them that small. And a lot of the space systems, the ones they're planning to send to Mars and the moon and that sort of stuff, are in the kilowatt size. You start competing with what are called legitimate nuclear batteries, where instead of having a critical power source, you have, say, a radioactive material that makes heat, like cesium or plutonium-238, which is what they put on space probes. And so you just get like a coffee container full of something hot, and you use that to generate power. So yeah, there's a nuclear solution from almost no power to some of the ones, 1,800 megawatts is what some of the European designs are up to. Everything in between. So multiple orders of magnitude, right? That would be on the order of 5 orders of magnitude in power. But the tiny kilowatt ones are interesting. They stop being fissile systems under 100 kilowatts, I think.
So
I'm
nuclear
wondering-
submarines, what size power plant are those, and why have we deployed something similar to that elsewhere?
My official guidance for my company is to go, they put reactors on submarines? Wow. I didn't know that. In a less facetious response, that is literally, I'm supposed to express ignorance of the nuclear Navy. They are literally SMRs, but they are very specialized. And so imagine the difference between having a Ford F-150 pickup and the McLaren F1 racer, right? Those are different designs for different products for different areas. And one of them is cost is no object, and one of them is cost first. That's almost literally the difference between those kind of systems you can imagine. Again, I didn't necessarily hear that from me. But yeah, they're completely different systems. They would qualify as SMRs. You can look up on different sites and see what estimates are for their performance. Fascinating technology. Not really something I'm commenting on.
We have 2 questions in the chat. One of them, Barry asks, what countries are far ahead of the U.S. in deploying SMRs?
Far ahead, I'm not sure anybody's far ahead. The Chinese have deployed an HTGR, and they are gaining experience with that. The Russians have continued to operate liquid metal reactors. They tend to be bigger now. So there are other countries that are in that field. I think the Chinese are probably the ones who are most interested in developing the technologies. The British are working with that with Rolls-Royce. There are some others around the world as well. But the U.S. has probably got the most active commercial efforts to develop different reactors right now.
Okay, and we have one more question in there, then we'll get to your question, Ted. Are older design nuclear power plants dead?
5 years ago, I would have thought yes, because of all the trouble getting the Vogtle reactors up outside of Atlanta. The discussions with the changing energy grid, data centers, and all that. Some of these people are saying, "Hey, I want 1,000 megawatts." Well, you don't typically do 1,000 megawatts with an SMR. You can do that. You get a full size one, buy enough units, sure. But if I just want the quickest, easiest solution to 1,000 megawatts, I would probably go to Westinghouse and ask them, could you build me another one? And ask how they would control the cost, some of the lessons they've learned. So I think that the demands on the modern grid may bring back a couple of projects. They're talking about finishing the VC summer plants. That's active discussion now. Those are shut down because of cost overruns and trouble with the mega project issues. But those may come back. And so if those come back, then yeah, that's a viable technology again.
The question is there some method of applying some sort of, I don't know, energy emergency legislation or something like that that can at least protect those former plant sites, which then could eventually become foundations for future sites?
Yeah. Once they're gone, I think they're gone.
Yeah.
We see folks in like the West where they're having a bit of an energy crisis now. We worked with one of the companies in Wyoming, and they're concerned about reliability first, right? They don't want the power going off in January and freezing people to death or out of their homes or all that kind of thing. They have a little bit different take on what a reliable grid looks like, and they don't necessarily put clean in front of reliable. They're not eager to shut down units and things. So they are tending to value that combined property. I was talking about putting renewables and nuclear together to get a better grid overall. It may not be the lowest cost one, but it's the one that's going to serve their customers the best. And it's sort of that realization that there may be something better than low cost of electricity